Hello, good people. I'm Trockers. Welcome back. So, in today's lesson, we'll solve a ZIMSEC November 2011 paper 2 question on vectors, focusing on planes and lines. Okay, it reads 6a. Show that the perpendicular distance from the origin to the plane with equation r dot 4I plus 3j minus 5k equal to 10 is square root of 2. B item 1, find the vector equation of the line L1 which passes through the points 1, 0, 2, and 3, 1, 0. Item 2, find the coordinates of the point of intersection of the line L1 and the plane whose equation is r dot -1, -1, 1 equal to 1. Then item 3, the line L2 has an equation r equal to 210 plus lambda 423. Find the acute angle between the line L2 and the plane pi, 7 points. So in total, this was allocated 10 points. Okay, let's go ahead and get started. All right, so this is 6a. Right. So we want to show that the perpendicular distance of from the origin to the plane with equation r dot. So the equation is r dot 4I plus 3j minus 5k, right, equal to 10. So this can also be written as r dot 4, 3, -5 equal to 10, right? So we are going to use point to plane distance formula. So remember, the formula should be okay, let me write it in full. So the formula should be distance equal to ax naught plus bx naught plus cx naught plus d over that's the normal vector here. So over this, right, over square root of the normal. So what's going to take place here is that since it's from the origin, which is 0, 0, 0, 0. So if you plug in 0, 0, 0, here it's supposed to be minus d. I'm sorry. Here it was supposed to be x naught, so minus d. So since it's 0, it's going to be that over that. So guys, always know that it's always d over a normal vector. That's how we find the distance from the origin to the plane. So now our distance equal to d over n, and remember n here is equal to 4, 3, -5, right? So our d is this constant here. That's our d. So it's going to be 10 over square root of 4 squared, that's 16, plus 9 plus 25. So here it's 10 over square root of 50, which is 10 over 25 times 2, that's 5 root 2, which is 2 over root 2. When I rationalize, right, it's going to be square root of 2. So this is what we are supposed to show. That distance there, it's square root of 2. Okay. Then 6b item 1. So 6b item 1, we need to find the vector equation of the line L1 which passes through that the points 1, 0, 2 and 3, 1, 0. So we have the points 1, 0, 2, right? I can call this A. Then I can call this 3, 1, 0. I can call this B, right? Position vector there is B. So we know that the equation of a line should be R equal to any point on the line, right? Okay, sorry. All right, so R equal to any point on the line plus lambda, the direction vector. So it depends with what you have made A and B there. So I'm going to calculate the direction vector here. So my B is OB minus that 3 minus 1, 1 minus 0, 0 minus 2. So I'm going to use 3, 1, negative 2. So it's not 3, 1, negative 2, but 2, 1, negative 2 there. All right, so I'm going to use this. So the equation that I'm going to use is going to be R, right, equal to, I will use 102 plus lambda, right, 2, 1, negative 2. So here, in general, let me just say, you could also use either B or A. So you could also use R equal to, B is what? 3, 1, 0. So here it's plus or minus lambda 2, 1, negative. So it depends, because if you subtract, if you find BA, you're going to get a negative here. So any of these answers is correct. Even for the first one, right? Even for the first one again, if you write it like this, R equal to 102, right, plus or minus lambda, obviously you pick one there, 2, 1 minus 2, any of the answer choices there is okay. So that's the vector equation of the line passing through the points 102 and 310, but I will use this one here, okay? So now B2, okay, so 6B2, on 6B2, we need to find the coordinate of the point of intersection of the line L1. So for me, for L1, I used R equal to 102 plus lambda 2, 1, negative 2. So that's the one that I've used before. Then, so I use this, right? Then we also have, we are given the plane R dot negative 1, negative 1, 1 equal to 1. So to find the point of intersection, the coordinate of the point of intersection between the line and the plane, we find the general coordinates of the line, which is equal to 1 plus 2 lambda, then 2 minus 2 lambda. Then we plug this into the plane. So we have 1 and 2. So if you plug 1 into 2, it's going to be 1 plus 2 lambda, 2 minus 2 lambda times negative 1, 1 equal to 1. So we solve. So when we solve, we get negative 1 minus 2 lambda minus lambda plus 2 minus 2 lambda equal to 1. So negative 2, negative 2, negative 2. So negative 5 lambda, then negative 1 plus this, that's 1, right? Negative 1 plus that, I'm getting 1 here, right? So negative 1 plus 2, that's 1 equal to 1. So lambda is equal to, 0. So when lambda is equal to 0, so therefore the coordinates are, so now I need to take that. So if I plug in 1 plus 0, it's going to be 1, 0, 2. So the coordinates are 1, 0, and 2. Right. Okay. Then we move on to item 3. So on item 3, we need to find, we are given the line L2. So L2 equal to 210 plus lambda 423. So our direction vector there is equal to 423, and the plane pi, it is R dot negative 1, negative 1, 2. This was 1, sorry. Negative 1, negative 1, 1 equal to 1. So our normal vector is equal to negative 1, negative 1, 1. Right. So guys, let me quickly draw this. So we have our plane here, right? And we have this line that is within the plane. Okay. So this line, that's the direction vector. Then we have the normal in the what? In the plane here. Right. Then remember, okay, something of that sort. All right. So we want to find the angle between the line and the plane. So the angle between the line and the plane is theta. But if we calculate now, we are going to find alpha, which is the angle between the normal and the direction vector. But once you get alpha, the required angle is going to be 90 minus alpha. But instead of us going this long route, we just use, both here we use cosine, right? If you find the angle between the normal and the direction vector. But for this one, we just use sine, since we know that cos 90 minus alpha is just equal to sine alpha. So let's just go ahead and use sine for this part here, right? So to get the desired answer, since we are looking for the acute, it means you're going to eliminate the negative. So sine theta is equal to, right? So it's going to be the dot product, right, over the absolute, over the modulus here. So we just take the absolute, which is the positive, right? So now on the side, let's find d dot n. It's 1, 4, 2, 3 dot negative 1, negative 1, 1, which is minus 4 minus 2 plus 3, which is minus 6 plus 3, which is negative 3, right? Then we have square root. Okay, so if we find this, it's going to be 16 plus 4 plus 9, which is root of 29. And also we have a modulus for the normal, which is square root of 1 plus 1 plus 1, which is root of 3, right? So therefore, our sine theta equal to, remember, we are taking the absolute. Okay, let me just do it. Absolute of negative 3 over root of 29 root of 3, which is just 3 over root of 29 root of 3. So the acute angle is going to be arc here. It simplifies, it implies that it's arc sine of 3 over root of 29 root of 3, right? So if we find that arc sine of 3 over square root of 29 square root of 3, I'm getting, sorry, I'm supposed to be in degrees. All right, I'm supposed to be in degrees. Okay, so it's 18 point, so I'm getting 18.7617566, right? So therefore theta equal to, since the degree of accuracy is not specified, and in terms of angles, we are supposed to give it to the nearest, so is equal to 19 degrees to the nearest, no, to 1 decimal place. I'm sorry, not to 2 significant figures, but to 1 decimal place. So it's 18.8 degrees to 1 dp, because for ZIMSEC, they require us to leave it to the nearest 0.1 degrees. So guys, that's all about this question. Let's continue to do a lot of practice. I will see you in my next video. Take care.